Okay, so in this class, we'll be talking about how bonding and orbitals, concepts that you learned about in the past 3 semesters here, can then be applied to beyond organic chemistry and to chemistry across the periodic table. But what I want to do is first do a quick review of the different bonding models that you should know for this course. So one of them is the so-called valence bond approach, which is what we use to make Lewis dot structures. So I'll just go over what, quickly, I know you all remember this, so we'll just kind of quickly go over what you should be able to do for this course. Okay, so the main point of the valence bond approach is that it assumes for covalent bonds that we have pairs of electrons within the bond between atoms. And these are located in your atomic orbitals. And this is what forms the bond. AOs is atomic orbitals. And then you can also have pairs of electrons within lone pairs that are also located within atomic orbitals on the separate atoms. Okay. So obviously, this isn't enough to govern all the chemistry that we'll be doing, so we'll be talking about other models as well. But what you need to know for applying this towards the valence bond approach is you should be able to review the octet rule. And then also know when to expand the octet. Maybe the more critical point that we should do first is we need to know the number of valence electrons. Number of valence electrons, VE. So these are the electrons that are going to be involved in bonding because they're in the outermost shell. So you also need to know your kind of simplified electron configuration. So for example, carbon has the electron configuration of 1s2, 2s2, 2p2. In the outermost shell, what this means is that it has 4 valence electrons that are involved in bonding. The 1s2 electrons are, of course, they're within the 1s shell. They're close, really near the core. They're not far enough to kind of be shared with another atom for bonding. So we only consider these. And then you could simplify this expression if you wanted to as something like this. Great. And then other thing that you need to know will be you'll need to know resonance structures, which I'm sure you guys are all experts on from organic chemistry. Resonance structures and formal charges. Keep in mind again, formal charges are not oxidation states and they're not actual charges. They're just a simplified way to kind of let you know which contributes most to a certain resonance structure. Okay, so let's do an example. ClO2 minus, the chlorite anion. So this has 20 valence electrons, 20 VEs. And we know this because chlorine is in group 7 valence electrons. Oxygen is in group 6. So we have overall 19 electrons plus an additional electron for this 1 negative charge. And when we want to draw the Lewis structure of this molecule, we draw our atoms, we draw our bond, so 2 electrons in each for the covalent bond, and then we finish filling out the number of electrons, paying attention to the octet rule. So in this structure, we have a filled octet for each of the 3 atoms, and then we can do formal charges. So oxygen has 6 valence electrons, but here we have 1, 2, 3, 4, 5, 6, and then 1 electron from the bond, 7 electrons within this thing. So 6 minus 7 is minus 1. This other oxygen is the same, minus 1. And then chlorine has 7 valence electrons, but here we have 1, 2, 3, 4, 5, 6. So that's 6. 7 minus 6 is plus 1. So overall, this chlorine has a formal charge of plus 1. And then we could draw our other resonance structures. So chlorine is in the 3rd row, which means that it has the capability to expand its octet. Let me do the octet expansion here. So here, and then we still have these lone pairs. So in this case, chlorine has expanded the octet because it has 1, 2, 3, 4, 5, 6, 7, 8, 10 electrons around it. And then if we look at the formal charges in this structure, this will now be 0, formal charge. This will also be 0, but this will still be -1. OK. And then there's the other resonance structure that I'm not going to draw, where the double bond moves to the other side. OK, my comment on the expanded octet is sometimes some people invoke d orbitals as the reason why we can expand the octet. That turns out actually not to be the case. It's a handy way of thinking about it, because it follows the rule that if you have d orbitals, you can expand the octet, which is true. But the d orbitals are actually not involved in bonding in this case, because they're actually quite high in energy, so they're not involved in this octet expansion. So that hybridization rule that you might have seen before is not quite true. We'll talk a little bit more about what orbitals are actually involved in having structures like these later on in this course. OK, let's see. What else did I want to talk about? Nope, this is pretty much it. So practice your loose dot structures. We'll have some practice problems in the homework, but also there are plenty in the textbooks if you need to brush up. And happy to talk more about this in office hours.